All right. I will try to remember to record these lessons because I don't have very many lessons recorded for this, well, from here to the end of the course. I think I have 2 lessons recorded, and that's all. So here we're looking for area of this trapezoid. Let me do some rough sketches here, and you can tell me, is this a trapezoid, yes or no?
No. Yes.
Yes, trapezoid. So what is a trapezoid? Half a, could be half a hexagon. Okay, so let's, since we're not quite ready to define it, let's try another one. Is this a trapezoid? So what's a trapezoid? Still nobody's committing? Okay, let's try another one. Okay, 4 sides. Okay, that'll be important. Let's try another one. Is this a trapezoid?
That's a diamond. That's a kite.
This is a trapezoid. Yeah. What has been true about all of these? 2 parallel sides. Yep. So any shape that's a quadrilateral, so 4 sides, with 2 parallel sides is a trapezoid. So even if I did this one, it's also a trapezoid. But we have to be careful here because I've taught from some textbooks that would say this is not a trapezoid. But other textbooks would say it is a trapezoid. I would like to say it is a trapezoid because the area formula for a trapezoid works for this shape. And it has 2 parallel sides. So I would side with those mathematicians who say a trapezoid is a quadrilateral with at least 1 pair of parallel sides. There are others who would say, nope, trapezoid has to have exactly 1 pair. It can't have 2 pairs. But I would say it's kind of like square and rectangle. Every square is a rectangle, but not every rectangle is a square. Similarly, every parallelogram, I would say, is a trapezoid, but not every trapezoid is a parallelogram. Okay, so that's where I fall on this not very hot debate. So if we come back to sort of this kind of shape, this is what we have over there. So when we're finding the area, the 2 parallel sides, we call base 1 and base 2. And then this perpendicular distance between them is the height. All right. So over here, we have, do I have something to pull out? I think I do. Let's see what it looks like. We have this trapezoid. So base 1 is f of 0. Base 2 is f of 4, which I wouldn't have to write it in function notation, but I want you to make the connection. So base 1 is 3, base 2 is 5, and so when we plug that into the formula, and we have this h, which is 4, I'm going to get 16. And you also get 16? Yep. Okay. Is this the exact area under this line between the x-axis and the line? It is exact. All right. Now I want you to close up your notes. Because the next series of questions are just kind of building, and I want to get through the whole series with your full attention, and then I'll give you a good chunk of time to fill in any details that you want to write down. So for now, notes should be closed. No pencils, no pens, no cameras, no recording devices, well, except for this one. Oh, look at the board, look at the board, and look at me. But no, look at the board, okay? We're going to evaluate. Nope, we're going to skip that. That's just review. We'll jump to this since I introduced it already. So yesterday I referred to this idea of approximating an area by drawing rectangles. So I'm going to say the area from 0 to 4, so that's what we're asked for here. Area under this function, 1/2 x plus 3, same graph as we had above. So you know the exact area is 16. Is this going to be 16? No. Too big, too small? Too big, we have that extra stuff. So I built 2 rectangles. And I'm going to approximate the area using these 2 rectangles. Okay? So each rectangle has a width of 2. Okay? And the height of the first one is this f of 2, which is going to be 4. And the height of the second one is f of 4, which will be 5. Okay? Yesterday, as I drew it, I used the height on the first edge. So we could set this up so I have a rectangle that's here, and then a rectangle that's there to approximate the height. And that would be too small. Either way, we're going to end up at the same point. So it kind of doesn't matter which end I'm picking. So I've decided that for us, we'll just get in the habit of choosing the right end of the rectangle is going to hit the function. Okay, so here we have, for 2 rectangles, we could just look at it and say, oh, the width was 2. But if we think of what we're going to calculate, because we're going to do this multiple times, I'm going to take 4 minus 0, that total width, and then I have 2 rectangles, so I divide by 2. And that gives me the width of each one. So each one of these ends up being 2, so this width is 2. Good. The height of the first one, f of 2, we said is 4, and f of 4 is 5. So now we're going to calculate. So to find the area, I'm going to do the height times the width, plus the height times the width, adding my 2 rectangles, 18. Dun, dun, dun. How close are we? We're 2 off, because we know the area is exactly 16. Okay, now let's just look at this a couple different ways so that we kind of build towards a formula. Okay, so this 4 was the f of 2, and I should probably be drawing so people can see who are online. That 5 is the f of 4. Good. And then let's just scribble all over the place. Here we go. We'll try this again. So what I could do is I could factor the width out, because each height is multiplied by the same width. So the width is always the same. Good. Next, suppose I increase my rectangles to 4. So now my diagram is going to look like this. Again, my right end is going to hit the function. Okay, so the height is going to be a function value for each of these rectangles. The width, again, I'm going to do 4 minus 0, find that total distance. Don't use that. Let's use this. Total distance, and we're going to divide it by 4, because now we have 4 rectangles. So that's what I'll put in here. 4 minus 0, divide by 4. That'll give me 1. Each rectangle has a width of 1. Okay, we can see it easily enough, but again, we want to get to a point where we don't have to see the graph. We just know what's happening. So I get the width, and then the height of the first one is going to be 3.5. And f2 is going to be 4. and F3 is going to be 4.5, and F4 will be 5. So we have the 4 heights, and each of them has the same width. So when we calculate the area, we just do height times width plus height times width plus height times width, and so on. We get 17. Ooh, closer. More rectangles, closer to the actual area. But again, let's think formula. Where did this this 3.5 come from? That was f of 1. Okay, so there we go. F of 1 times the width, f of 2 times the width, and then 3, 4, and so on. And again, like we did previously, I could factor that width out. Good. Let's do 8 rectangles. There we go. 8 rectangles. Again, if I take the total width, that's a 4 minus 0, divide by 8, I now get 1/2. So there's the width is 1/2, and the height here for my first rectangle, this is going to be at 3.25, 3.5, 3 3/4, 4. So that's where each of these values is coming from. And then I ran out of space, so we could figure out the others, and I'll put them into the equation that we do here. So again, we're going to do height times width for each of these to calculate the area. There we go. Oh, but I just jumped ahead to add all the heights together and then multiply by the width. Good. So we already kind of derived it to this point. 16.5, we're getting closer with 8 rectangles. So again, this is just a reminder that the 3.5 is f of 0.5, and the 3.5 is the f of 1, and so on. Make sense? Okay. Let's work a little bit closer to the formula. This 0.5, here is one way we could say that we're calculating it. What I'm doing is I'm going to start with my left endpoint, and then I'm going to add the width, which is 1/2, one time. And that gives me this 0.5. Now, all of these, I set it up so it starts at 0, but suppose I wanted to find the area between 2 and 8. Well, it would be a little more complicated because instead of having a 0 there, I'd have to start with a 2. Right? So my first rectangle, I do the 2 plus 1/2, which would give me 2.5. And then I'd have to add 1 to it, or times 1, because that would be the first rectangle. Make sense? So where does this 1 come from? Talk to your neighbor. What's the calculation that we're doing to get that 1? Anybody? Yep. Exactly. So my left end, and I'm adding the width 2 times. And then my next one, start at the left end, add the width 3 times. Good. Next one, left end, add the width 4 times. And so on. Okay. So now let's look at if we had a curve like this, and we wanted to approximate the area with a bunch of rectangles. Given what we just did, and given this diagram where I have 4 rectangles, what's an expression for that value of x? Think about it. Talk to your neighbor about it. See if you can come up with an expression, and then we'll do it together. Anybody have an idea of an expression? Yep. So we're saying this is going to be A plus x over 4 times n. Think about it. Do you agree, disagree? Ramas? X minus a over 4? Well, why don't we kind of back up a little bit and maybe break this down into smaller pieces. So as we look back here, well, we already figured out this is the a value, right? So we know we want that a. What is this half? That's the width of the rectangle. So let's think about this, and I'll call it delta x, as being the width of the rectangle. How can we calculate that delta x? X over n? Not quite.
X2 minus X1.
Yeah, so b minus a over what? How many rectangles? N rectangles in total, so that's going to give me a formula for the width. Okay? So I'm going to have this width happening in this case 4 times. So I'll start with my a value, and then I'll add this width, b minus a over n, 4 times. Take a moment. Check with your neighbors, see if you can convince each other that that's true, or find if there's a mistake in that calculation. Okay, go ahead. So volume has died down. So how many people convinced that what we have in green here is correct? A few of us. Okay, some of us aren't convinced yet. So let's go back and look what I wrote up here. A is my left end. Delta x is the width. And 4 is the number of rectangles. So it means I'm going to start with this a value, and I'm going to add the width on 4 times. So I start with the a value. There we go. There's a. Add a width, add a width, add a width, add a width 4 times. So this correctly describes what that x value would be. Yeah, sure, yeah.
4b and n.
No, because n, if that was n, then we'd be at this end. Right? Because we have n rectangles in total. But I'm just looking at this point. Okay. Suppose we didn't know that this was the 4th rectangle. What if we said it's the ith rectangle? Then we would change this 4 to an I. And what we're going to do is we're going to say here I is 1, and here I is 2, here I is 3. You see how this is connecting to yesterday, where up here this is a series. And we're working this out to a point where we can get i's showing up in our series. So we can develop a formula that we can use those ridiculous sum notations to actually calculate what this would be. So again, still no notes, but here we're going to do it with n rectangles. Okay. So the width of each rectangle as, do I want all this? Yeah, I'll pull it all out, and then we'll talk about each piece. So we're still thinking about the same function, and I think this is the function. Yep. So this is the question. We want to find the area under this function 1/2 x plus 3 between 0 and 4. Good? And again, where we came up with this 4 is that's my right end, 4, minus my left end, 0. So that is my total width of the whole zone I'm trying to figure out the area of, and I divide it by the number of rectangles, and that gives me the width of each rectangle. Okay, so if I come back to this page at the bottom, that is this calculation. So I did 4 minus 0 over n, that gives me the width of each rectangle. How are we doing? So far, so good? Let's look at the next piece. Here, this 4 over n is the width times 1 for my first rectangle. So I have one rectangle's distance that I've gone to the right. Here I have 2 rectangles distance. So I've done the width of the rectangle twice, width of the rectangle 3 times, and then some mystery point in the middle, width of the rectangle I times. So just a reminder, we're getting this from the left end. Let's do this. My left end is 0, my left end is 0. Plus the width of the rectangle multiplied to whatever my rectangle number is. Sharia.
The height of the nth term is the final one?
Yep, that's going to be the height of the one on the right end. So if you came back here, that would be this height at that end. Take a moment. Ask your neighbor any questions that are hanging around in your head up to this point. Anyone have a question for me? Daniel.
If you were to hypothetically say that the function that we were looking at in total had 8 rectangles in it.
Yep.
Would the height of your I term be for every rectangle up until the 7th rectangle, since the nth term is the last rectangle?
Yeah, this is just a general term. So this is any general term. We could pick our I value. If my I value is 1, then I would get this. If my I value was 8, and we said that was the last one, then this would be that value.
So then the I term only applies for everything up to the 7th, right?
Well, even including 8. So I is going to be kind of, if I have 20 rectangles, I could be anything from 1 up to 20. Yep, could be the last one. We're just looking for something to describe a general rectangle that's mysterious. We don't know which one is in the middle. We don't want it to be the last one, where that would be an N. We don't want it to be the first one. We just want it to be something in between. Good? Okay, so again, this 4i over n comes from my left end, which was 0, plus the width of the rectangle. I'll come back to this. So my left end, which was 0, the width of the rectangle, which is 4 over n, and I times, where I could be 7. If I had 20 rectangles, it could be 18, could be 13. It's just any number. Hello.
I was trying to be so inconspicuous, but it's really hard when you walk in front of everyone.
That's for me. Back to recording. Okay. So far, we're good? All right. We want to come up with an expression for the area under this curve. So under this curve, there we go. If I have a mystery number of rectangles, n rectangles, I don't know how many I'm going to have. So this is building a formula. Okay. So here's my area calculation. So I'm going to have the height of each rectangle, which is the function value. I'll add them all up, and then I'll multiply by the width, because the width is a common factor. Right? So what I can plug in here is this will be 4 over n from that first term, and then this will be 8 over n from the second term, and this will be 12 over n from the third term, and then this is going to be 4i over n for my mystery ith term, somewhere in the middle. And then my last term will just be a 4, because those n's would cancel out, because that's my right end. Good? Well, I need to figure out these function values. I don't have a graph to just look at and say what they are like I did in the previous questions. So I actually have to plug it into my formula. So this formula that I had here, that's what I have here. And I'm going to plug in the 4 over n, the 8 over n, the 12 over n, the 4i over n, and then just the 4 once I get to the right end. Good? Okay. Now, let's see if we can simplify this down a little bit. Because again, we're working towards getting a general formula. With all of these, you will notice we have plus 3, plus 3, plus 3, plus 3, plus 3. How many 3's do we have? N 3's. So we can take that out of this bracket and say that we're going to have all of these N 3's, but when I take it out of the bracket, it still has to be multiplied by that common factor. But I've separated it out as its own separate term. And then inside the bracket, I still have this, I've simplified a little bit. Half of 4 over n will be 2 over n. Half of 8 over n is going to be 4 over n. 6 over n. Half of that will be 2i over n. And then half of that will be 2. Good? All right. Notice that all of these, maybe I'll just change this one again to be 2n over n. Well, actually, it was a 4n over n, right? Oh, divided by 2. It is a 2n. Thank you. So 2n over n. Because if I do that, then I can see I have an n, common factor of n in the denominator. Let's factor that out. Yep. Oh, sorry, over here? Over here? Hey. Oh, so I have all this stuff that's multiplied together. And then this piece comes from factoring out all of these 3's. So I factored the 3 out, and then I multiplied it to the n over 4 to make it a separate term. Because inside here, they're all getting multiplied to that 4 over n. So when I take them out, they all have to get multiplied to that 4 over n. 4 over n times. Oh, because, sorry, I'm not just factoring it out. Good question. What I'm doing is I'm saying I'm adding 3, 1, 2, 3, however, n times. So I have n 3's inside this bracket. So I'm just pulling the n 3's outside of the bracket. Good? Good with this line, this last line I have up there? All right. Now, guess what this is? We could summarize it with sigma notation and say our area is the sum from I equals 1 to n of I, right? And then all of this is being multiplied to this 8 over n squared. I'm just going to put it in front because it's going to get multiplied. And then we'll have the 12 added at the end. All the steps logical so far, even though as we look at this, it's kind of crazy, but all the steps to this point make sense. Well, what is this sum equal to? Eight over n squared. Yep, this is one of the sums we looked at yesterday. I put it on the board here because I always need a reminder. N times n plus 1 over 2 plus 12. Let's simplify this a little more. We'll have our area is equal to 8n squared. Oh, let's reduce that first. Let's say 2 goes into 8 4 times. So then we'll have 4n squared plus 4n. Each of them is over n squared plus 12, which is 4 plus 4 over n plus 12, which is 16 plus 4 over n. So suppose our n value was 2. What would our sum be? 18. That's the first question we did with 2 rectangles. Then we did 4 rectangles. 4 over 4, 1. 16 plus 1, 17. That was the 4 rectangles. 8. 4 over 8, a half, 16 and a half. Infinite rectangles. We get the limit as n approaches infinity of 16 plus 4 over n, which is 16. We get the exact area. Dun, dun, dun. There we go. I'm going to stop here. What do you need to put in your notes? What's going to help you? I'll scroll up to the top here. I think what I'll do is, let's do pause. Anyone have a question before we move on to an example where we put this all into practice? Yep. So over here, this part that's circled in blue, this part here, that comes from all of these 3's that are inside the bracket. I have n terms, so I have n 3's. When I factor it out, it has to get multiplied to that common factor, and it becomes its own separate term then. Is that good? Sharia? Okay, we'll get there in a moment. Daniel? And in the first step, third step. Oh, to go from here to there? Yeah, each term has an n in the denominator, so I factored out that n from the denominator and multiplied it to the 4 over n, which gave me an n squared down there. Okay, next page. So here's a formula. And if you remember back in chapter 1, what did we do in chapter 1? We did limits. And we did limits eventually to find slopes of tangent lines. And then we kind of took a detour to do all sorts of limits just so we got familiar with limits. And then in chapter 2, we discovered, oh, there are some shortcuts. So we don't always have to go back to the definition of the derivative. Similar idea here. This is like the limit stuff, which is long and complex. After this, we're going to find some shortcuts. Okay? Do expect to see one question like this on the test. And when we get to the test, you'll be given this formula that we'll explain in a moment. But inside that formula, we have these two things calculated. I do not give you those on the test. So you need to know how to calculate those. So let's talk about them. This delta x, remember, that's the width of each rectangle. Good. And then this x with the subscript I, that is the x value on the right edge of the rectangle. And we need to know that in order to calculate the height on the right edge, right? So inside here, this f of x subscript I, that's a height. And then this, let's go blue again, is the width. So I have a width times height. That's giving me an area of each rectangle. We add them all up, and then we take the limit as though we had infinite number of rectangles. So we're going to do that for this function. Width, there we go, width. Some days I can spell, some days I can't spell so well. I was trying to think of something else that would rhyme, but I drew a blank. All right, here's a visualization of what we're doing. We have this curve. We're going to find that shaded area. So those two things that are not given on your formula sheet or not given on the test, I need to figure out an expression for the width of each rectangle and the ith term, or that x value for the ith term. So the width, remember, is right end minus left end divided by number of rectangles. That's written above, but I wanted to remind myself. And so in this case, I'm going to have 3 minus 1 over n. So my delta x is 2 over n. There's my width. So far, so good. For my x value, I start at the left end, and then I add delta x to it I times. So understanding where these come from will help you remember what to do. So in this case, xi is going to be 1 plus 2 over n times I. So what I'm going to do is I'm going to, kind of like the previous question, I'm going to ignore the limit until I come with a simplified expression, and then just stick it in at the end, because it just gets so tedious to put it in. Okay, so maybe the way I'll indicate this is I'll do Sn, I'm going to do the sum of n terms. So I'll have the sum from I equals 1 to n of f of xi, I guess I'll just stick it in as in the formula for now, times the delta x. Xi is 1 plus 2i over n. That'll go into my function, multiplied by 2 over n. Oh, I want to pause for a second. So I've never taught those first 3 pages the way I did today, where I had you put your notes away, and then we went through the whole thing, and then I let you write things down. Was that good, bad? What's your feedback on that? Good? Okay. I thought it would be, because you can get bogged down in the earlier questions if you're trying to write down and follow. So, okay, thank you. If you have other feedback, let me know. Okay, let's do a couple things now. I'm going to have the sum from I equals 1 to n. This 2 over n doesn't have any i's in it. So I'm going to factor it and bring it in front of my summation. And then I'm going to plug this into my function, which is x squared plus 2x plus 1. And I substitute xi in. And now I work at simplifying this. So I'll need to do some expanding. So I'll keep the 2 over n. That's a weird one, but I can live with it. When I distribute that, I'll get 1 plus 4i over n plus 4i squared over n squared. Good with that? Distribute the 2 in, 2 plus 4i over n plus 1. We're good? Now I'm going to collect like terms. So I have 4i squared over n squared plus 4i over n and 4i over n, 8i over n, 1 plus 2 plus 1, 4. This should look familiar. You did questions like this yesterday. I'm going to give you a 5-minute head start, and then I'll get writing the rest. Once you have it all simplified down to an expression with n's in it, then take the limit as n approaches infinity. If you were following along as I silently did work, you hopefully noticed a mistake that was showing up along the way where I lost track of that 3. So I added it here and multiplied it in the denominator, and then that results in each of those having a 3 in the denominator, which carries into the next line as well. So that's a mistake that I made. But then from here, once we get that expression with just n's, we found an expression for the sum of n terms. Sum of n terms. Now I'm looking for the sum of infinite terms, and often we don't put that infinity with the s. We'll just put the s to represent an infinite sum. And we get that by finding the limit as n approaches infinity. Every term with an n in the denominator goes to 0. So what we're left with is the 16 plus 8/3, which simplifies down to 18 2/3. There we go. That's all we have time for today. I guess if you're online and you have the notes, I could quickly go over my answer to the next question so you can compare, as long as you have the notes. Okay, so again, we need to figure out the width of each rectangle, that's delta x, and the x sub I term, because we're going to use that to calculate the height of each rectangle. And this is what it looks like when we plug it into the formula. All right. Then, that 3 over n is a common factor. I'm going to take it out in front of my summation. And then I expand the brackets, and then I will collect the like terms to give me this. Once again, because I have 3 summations, that n over 3 gets multiplied to each of the summations. I want to do one more step, which is to get rid of any number that's multiplied or divided to an I. So that takes us here. And now we can apply those formulas that we looked at yesterday. The sum from I equals 1 to n of I is this n plus times n plus 1 all over 2. And the sum for this I squared is going to be this expression. Those I would give to you on a test or quiz. Then we'll do some simplifying. There we go, expanding to get rid of those brackets. At this point, I could already take the limit. I'm guessing that I didn't. Well, let's see, did I collect like terms? No, I took the limit. There you go. Why not? So up until this point up here, I was doing the sum of the first n terms. Here, I'm doing the sum of an infinite number of terms, which gives me this final answer of 18. Dun, dun, dun. And of finding the area under a curve using an infinite number of rectangles.